Okay, let us start my presentation. I am Takeshi Kitahara, a professor at Kanto University from Japan. Today, I'd like to talk about seismic performance of steel bridge piers corroded at the corners and bottoms for several earthquake motions. Here is the outline of today's presentation. I'll start by giving the background and objectives. Next, I will show target structure and analytical model, and as the analytical conditions, I show the corrosion damage and input motions. So, I will show some results. Finally, I summarize the conclusions. First, background is here. Corrosion has been considered to be one of the most important type of damage on steel bridges. It occurs mainly at the corners where the coating tends to be thin, and at the bottoms where stagnant rainwater tends to be generated. The further progress of such corrosion damage results in reduction of the load carrying capacity of the piers due to cross-sectional loss, and thus their seismic performance is decreased. Moreover, it may also lead to significant damage such as cracks and ruptures. As the previous study, we carried out a static experiment and finite element analysis of rectangular steel bridge piers with corrosion damages at the corners, subjected to two-dimensional horizontal ground motions. On the other hand, few studies have focused on the effect of corrosion damage at the bottoms. The maximum bending moment during earthquake acts on the bottoms. Hence, it is also important to investigate the seismic performance of steel bridge piers with corrosion damages at bottoms. At the same time, uncertainty in input ground motions may also affect the seismic performance of steel bridge piers. So, as a consequence, the objective of this study is to investigate the influence of the corrosion damage location, corrosion damage ratio, and uncertainty in the input ground motions on the load carrying capacity of the steel bridge piers. Here is the target structure used in this study. We consider the T-shaped rectangular steel bridge pier designed by the old seismic code in Japan, which was used in high economic growth period. The description of the target pier is shown in the right top figure. The original length of target pier is about 9 meters. The bottom two figures show the corrosion damages in the steel bridge piers. The left one shows the corrosion damages at the corners, and the right one shows the corrosion damages at the bottoms. The target bridge pier is modeled by the finite element model using shell elements. The description of the structural parameters and material properties are summarized in these tables. The length of analytical model is 5.3 meters. The wide thickness ratio parameter is 0.686 and the slenderness parameter ratio is 0.442. So, it can be seen that this pier is a seawall structure and is prone to local buckling. The material properties are used as a general steel materials. Here, I will explain about how we consider the effect of the corrosion damages. We consider the three cases. The first case is that the corrosions happen only at the corners. The second case is that the corrosions happen only at the bottoms, and the third case is that the corrosions happen at both corners and bottoms. For these three cases, we consider the corrosion rates such as 0%, 25%, and 50% are considered. The volume of the corroded parts and the volume loss ratio are summarized in the tables. Even when the corrosion rate is the highest at 50%, the volume loss ratio is as small as 1.3%. Here, the first four natural periods are summarized. Since the natural periods for the case with corrosions only at the bottoms and the case with only at the corners were almost similar, and thus only the result of the case with corrosions at the bottoms are shown in the top table. It can be seen that the first mode natural period is about 0.61 seconds. On the other hand, the bottom table summarizes the natural periods for the case with corrosions at both corners and bottoms. It can be seen that the natural periods are slightly changed from the case with corrosion only at the bottoms, only when corrosion rate is 50%. In order to consider the uncertainty in the input ground motions, we consider total 12 observed earthquake records, including 6 NS components and 6 EW components. These two figures show the acceleration response spectra of these earthquake records. It can be seen that the response spectra vary each other, and Tsukidate records show the peak value at short period compared with the other records. And Maxi record shows peak at the 0.6 seconds, which is the same time with the first natural period of Piers. Here, acceleration time histories of two records, such as the Machi-Machi-Miyazano records observed during Kumamoto earthquake and the Tsukidate record observed during Great East Japan earthquake, are shown for both NS and EW components. It can be seen that Max records are short-time duration and the Tsukidate records are long-time duration. Okay, now let us show the results. This figure shows the horizontal load displacement relationship at the pier top for each input ground motions. In these figures, the horizontal loadings and horizontal displacements at the pier top are divided by the horizontal yield load and horizontal yield displacement respectively to make them dimensionless. The elastoplastic behaviors of the analytical models are almost similar. Moreover, the overall load displacement relationships don't significantly change irrespective of the corrosion damage ratio for all of the corrosion damage cases. Next, these figures illustrate a comparison of the maximum displacement and maximum loading by the corrosion damage ratio. Note that the percentage changes in the maximum displacements and maximum loadings according to the corrosion damage ratio are also shown in these figures. At the same time, it can be seen that the changes ratio depends also on the period input ground motion. In particular, the maximum displacement decrease at the corrosion damage ratio increase for the case with the Machi-Machi-Miyazano April 14th records. One of the reasons for the results may be the relationship between the change in the natural period of the analytical model due to corrosion damage and the dominant period of the Machimachi-Miyazono April 14th record. Finally, in concluding, the following points are made. Number 1. The results demonstrate that the maximum displacement increase and the maximum loading decrease as corrosion damage progresses. These tendencies are similar to those in the previous study. Number 2. It is also confirmed that the change rates of the maximum displacements and maximum loadings depend also on the input ground motions according to the change in the natural period of the analytical model, due to corrosion damage and to the frequency properties of the input ground motions. Number 3. Furthermore, it is found that the change rates of the maximum displacements and maximum loadings for the case with corrosion damage at both the corners and bottoms are capable to be roughly estimated by those for the case with corrosion damage only at the bottoms. Thank you for your kind attention.